Hello, this is Mr. Huber. In this lesson, we're going to learn about solving linear systems of equations through the graphing method. Before we get into systems of equations, let's go over some information that's going to be particularly useful that we should know and can recall and apply to what we're doing with these systems of equations. Okay, a solution of an equation. If something is a solution, it's values that make the equation true. And when we graph something, we're graphing all of the solutions for an equation in two variables, right? We have a bunch of points, x comma y is typically when we're graphing, two variables, and we connect those with a line. And that graph is all of the points that make the equation true. It's all the ordered pairs that would make the equation true and make up the graph. And a linear equation, recall, can be graphed using a y-intercept and slope. So y equals mx plus b. We're going to see that in the form we have when we're graphing these lines. We're going to graph a y equals mx plus b and another y equals mx plus b. That's what a system is. Okay. So what is a system and how can we solve it? A system of equations is two or more equations in the same variables. Now we're only going to solve systems of two equations, but it's possible to solve systems with three or four or even more. Okay, and they have to be in the same variables. So we wouldn't have an equation like 4x plus 2y equals 8 and then 3a plus 5c equals 20, where they have two different variables in the two equations. So they have to have the same two variables. Again, typically when we're graphing, we're using x and y. We'll see that in our examples coming up. The solution of a system is the solution that solves both equations in the system. So it'll be the one point that is on both lines. That's how we can use graphing to solve a system of equations. Okay, we can use graphing to solve a system of equations by graphing and finding the one point, the ordered pair, where the graphs intersect. Okay, because that would be the one point that's a solution on both lines. It's the only ordered pair and point that solves both equations. That's what the solution of a system of linear equations is. The ordered pair that solves all of the equations in the system, and in this case, the two that we're going to work on. And that will be the solution for the entire system if it's the one point that they have in common. So let's see what that looks like with some examples. So here we have a linear system of equations. So it's two equations with the same variables. We have an x and a y in this equation, we have an x and a y in this equation, and these two are already solved in y equals mx plus b form. So we don't have to do any work to get the y by itself, we just graph it using the slope and y-intercept. So we'll graph one equation at a time. So we're going to graph this equation here first. With a y-intercept of -7, so we go to our y-axis and put a point at -7. Then our slope is 1 over 1, right? 1 over 1. So I'm going to rise 1 and run 1, rise 1 and run 1, and I can keep doing that forever, and I can draw a line then that goes through those points. So that would be the graph of that equation, y equals x minus 7. Now we'll take the equation y equals -1/4 x minus 2. So we've got -2 as the y-intercept. We go down 1 over 1, 2, 3, 4. I think we can see down 1 over 1, 2, 3, 4. And you could go up 1 and left 4. Okay? It doesn't matter when you have a negative fraction. Remember, for slope, if you go negative and then positive, or you go positive then negative, one of the numbers is negative. So we have an equation then that we can graph through those points, and we can see where they intersect. So it looks like this point right here is the intersection. That's at 4 comma -3. So 4 comma -3. We can check that then after we graph it, because especially when we're graphing by hand, we may not always get exact graphs. We're going to want to make sure, and anytime we solve any kind of equation or system, we want to check our answer if we can. So we're going to first check 4 comma -3 in the first equation. So we're going to put a -3 in for the y equals 4 minus 7, right? We took the 4 and plugged in here for the x. We took the -3, plugged in here for the y, and we get -3 equals 4 minus 7. That gives us -3 equals -3. That works. And now we want to check in the second equation, so we're going to replace the y with a -3 equals -1/4 times x, which is 4 minus 2. That's -3 equals -1 minus 2, so -3 equals -3. That also checks and works, so I know that 4 comma -3 would be the solution to that system of equations. Again, graph the system, find the point where they intersect. That's the one point that's a solution to both equations. I could take a point like this out here, -4 comma -1. And if I plug that into these two equations, it will solve this equation because it's one of the points that's on the graph for this equation. It won't solve this equation. And likewise, these points on the red graph would solve this first equation, but they wouldn't be solutions for the second equation, except for this one point. This is the one point that is a solution to both equations. So solving a system by graphing, get the equations in y equals mx plus b form, graph them and find where they intersect, plug that ordered pair back in to make sure it works in both equations. So let's try another example here. So we can do negative x plus 2y equals 3 and 2x plus y equals 4. So for this first equation, we're going to have to get the y by itself. So we'll do that work over here. We're going to first add x to both sides. So we get 2y equals x plus 3. You could have as 3 plus x. That's fine. It's no big deal. It's the same thing. And then I can divide both sides by 2. Okay, and I get y equals 1 over 2x plus 3 over 2. And let's solve the second equation for y, and then we'll go through the graphing. So we're going to subtract 2x on both sides. We're going to get y equals negative 2x plus 4. So let's graph that first equation. So we have y equals 1/2 x plus 3 halves. So plus 3 halves is 1.5. So we're going to go right there. Then we're going to go up 1 and over 2. Now keep in mind when I graph this from this point, up 1 from 1.5 goes to 2.5 and then over 2. And then I'm going to go up 1 and over 2. I can keep doing that, so just be careful with those fractions. You know how to get those graphed correctly. I could go down 1 and to the left 2. And so then I could have an equation here that I can graph through those points. So that would be my graph for that equation. Then we can graph that second equation in blue there. So a y-intercept of 4, and then I go down 2 and over 1. Down 2 over 1. I have the point right there. I can keep going down 2 over 1. And I could draw my line through those points. And I could see that I have a point right there, which would be the solution for this system. He said it should be. We're going to check it. We're going to plug it in. That's 1, 2. So if I plug that into the first equation, I'd get negative 1 plus 2 times 2 equals 3. That's 3 equals 3. That checks. And I could plug it into the second equation. I get 2 times x, so 2 times 1 is 2, plus y is 2 equals 4. So that's 4 equals 4. And that also checks. So I would know that that's a correct solution. So got to get the equations set as y equals mx plus b here, get the y by itself, then graph using the slope and the y-intercept, plot the y-intercept, use the slope for a rise and run, graph those lines and see where they intersect, and make sure you check those because, again, especially doing graphs by hand, not always the most exact, so you want to check and make sure that that solution actually solves both equations in the system. All right, another system of equations here, and you really should be doing this one on your own to see if you're grasping the concept. Pause as you go through each step. So solve these for y, then play the video to see if you've done that part right. Pause it again, draw the graph, then play the video to see if you've done that part again as you go through each section of how to solve this system of equations. Okay, so you should have done this part on your own, and let's solve these for y. So this first equation here, if I solve this for y, I'm going to subtract 3x on both sides. I get y equals negative 3x plus 3. If you have 3 minus 3x, that's fine. This second equation here, when I subtract x on both sides, I don't want to forget that I have negative y equals negative x plus 5. And then I'm going to need to divide by negative 1. So divide by negative 1 on both sides, and I get y equals x minus 5. So now I can graph these. So that first equation, y equals negative 3x plus 3, so I go to 3. I'm going to go down 3 over 1, down 3 over 1. I could go up 3 and left 1, as long as one of the numbers in your slope is negative when you have a negative slope. So I will draw my line through those points, and I've got that equation graphed. Now the next one, y equals x minus 5. So negative 5, I go up 1 over 1, up 1 over 1. I got a pretty good idea where my intersection is going to be, and I can draw my line through those points. And so I've got my second line graphed, and it looks like that's my solution. What should I do now? Well, I should be checking that. So I can take 2 comma negative 3 and plug it into both equations. Go back to your original equations. Always use your original equations. Plug these values into the original equations, not what you solved for over here, because you might have made a mistake in that part, and you don't want to plug your answer into a wrong equation. So in that first equation, I'm going to take 3 times x, so 3 times 2 plus negative 3 equals 3. So that's 6 minus 3 is 3 equals 3, and that checks. Now I check it in the second equation. I'm going to have x minus y. So I have 2 minus negative 3 equals 5. That's 5 equals 5 because minus a negative is plus, so that works. So I know that 2 comma negative 3 would in fact be a solution to that system. Get the equation, solve for y, get it in y equals mx plus b form, then graph those lines and find the point where they intersect. All right, before we see an application, let's take a billion break. A billion is a large number. Try thinking of a billion seconds. And the concept of that, how many days do you think there would be? Or do we need to measure it in years or less? So have an idea. What do you think a billion seconds would be in days or years or whatever you think it would be? Right? A billion seconds is almost 32 years. It's 31.7 years. So imagine this. I hand you a dollar. Next second, a dollar. Next second, dollar. We keep doing that every second. For you to get $1 billion, we'd have to do that for almost 32 years. Right? So it's easy to lose sight of, grasp the concept of how big a billion actually is. But that is a large number. So 1 billion seconds, almost 32 years. Here in this problem, we're going to have a business that rents inline skates and bicycles. They charge $5 per hour for skates and $10 per hour for bicycles. Yesterday, a group came in, they had 25 total rentals, each of them for an hour, and spent $210. We want to write a system of equations here with that information and use that to find out how many hours they rented inline skates and how many hours they rented of bicycles. So, a system of equations. Let's figure out what's something we know in this situation. We're going to want to define our variables first. So we're going to say x equals skates. Maybe use s for skates. I'm going to use x and y just so it's more familiar with what we've done previously. So x is skates, y is bikes. Okay? And we know that if they rent the skates and the bikes together, it's 25 total rentals, right? 25 total rentals. That's one situation we know from this problem. Another equation from the situation based on the amount of money. $5 per hour for skates, $10 per hour for bicycles, and spending $210. So that means if it's $5 for every skate rental plus $10 every bike rental, it's going to equal $210. So now we're going to want to solve this system of equations. We've written a system of equations in two variables. They both have x and y, two different equations from this same situation. We're going to solve and find what's the one x and y that solves both of those systems. It could be x is 1, y is 24 for this right here, right? I could have 1 plus 24. Or I could have 1 plus 24. But those wouldn't necessarily give me $210. So I can't just pick anything that works here. I can't pick just anything that works here. I have to find the one combination of x and y that works in both of these equations. So we're going to do that by graphing. And I'm going to graph this first equation using the intercepts, just as a reminder of another way we could graph linear equations. So the intercepts are when the other value is 0. So when I put an x value of 0 into this equation, when my x is 0, my y is 25. So my y-intercept would be 0, comma 25. And then I could put a 0 for y, and my x would also be 25. So in this case, both intercepts are 25. It's not always going to be that the intercepts are the same. In this case, they happen to be. And now I want to draw a line between those two intercepts. So I'm going to take my graph and draw a line between those two intercepts. So I've drawn a line using the intercepts, right? You can plug a 0 in for one variable to find the other intercept. Plug a 0 in for x, find the y-intercept, a 0 in for y, finds the x-intercept. And now we're going to graph the second equation. I could subtract 5x on both sides, so I had to get 10y equals negative 5x plus 210. And then I can divide everything by 10. I'm going to get y equals negative 1/2 x plus 21. So I have a y-intercept of 21. And I'm going to go down 1 and over 2, down 1 over 2, down 1 over 2, down 1 over 2. And I can keep doing that. I can see here they're going to be crossing, and I can draw a line through there, because really what I'm looking for is this point right here. That looks, it's at 8, comma 17. I should plug in 8, comma 17 to both equations. 8 plus 17 equals 25 if I plug it into this first equation. If I do 5 times 8, that's 40, plus 10 times 17 is 170. So that's going to be 40 plus 170 is 210. So that would solve both those systems. So that means they rented 8 skates for an hour and 17 bicycles. So 8 skate rentals, 17 bike rentals, and that gives me my solution to that situation based on writing a system of equations finding the points where their graph intersect, which is the only ordered pair that solves both equations in the system.